My name is Joel Myers. I'm an associate professor in the Department of Physics at SMU. I study theoretical cosmology and its connections to fundamental physics. Our study was aimed at measuring the absolute mass scale of neutrinos using cosmological data. Neutrinos are fundamental particles that are sort of mysterious within the standard model of particle physics. The way that neutrino mass plays a significant role in cosmology is that the presence of massive neutrinos results in a suppression of the clustering of matter throughout the universe. In other words, the presence of massive neutrinos causes the matter throughout the universe to clump up less than it would in the absence of those neutrinos. We utilized the High Performance Computing Center at SMU to conduct the data analysis that was a key input to our findings. We're looking for that suppression of matter clustering as evidenced through those data sets. But we found a surprising result. Rather than a suppression of clustering, what we found was that the clustering was enhanced. What this would imply is that neutrinos have negative mass rather than the positive mass that we know that they have. So this is a very surprising result, and our study focused on what could be explaining this preference for enhanced rather than suppressed clustering. What our study did was to look at recently released data from the Dark Energy Spectroscopic Instrument, or DESI, combined with observations of the cosmic microwave background, the CMB, which is often known as the afterglow of the Big Bang. And by combining data from those two sources, we were able to make a measurement of the absolute mass scale of neutrinos as seen through cosmology. If new physics is responsible for the signal that we found, it could lead to a different understanding of the physics of neutrinos. This means that physics beyond the standard model are required to explain new interactions that the neutrinos must have to either decay or interact with the dark matter that causes a change to their properties and their evolution throughout the universe. So in either case, we will need to change our understanding of the way that particle physics has its fundamental interactions, and this could be a modification either to the particles that we know about already, the neutrinos, or a change to the way that dark matter is understood.